Okay, so in this lecture, what I want to do is I want to talk about how to integrate trigonometric functions. So if you see the kind of like chapter 7's pattern, we're going to do techniques of integration. We started with integration by parts in 7.1. In 7.2, we're going to do the trig integration. So it's kind of like integrating trig function. I'm going to go through sine, cosine, the combination of them, the squares or powers of them, secant and tangent combination and powers. So kind of like you see all different cases of how to deal with trig functions. And then in integration, and we use that in 7.3, talk about trig substitution. So I think this sequence of topics, you're actually going to flow very well. Hopefully it kind of one leads to the next one and you can see how to solve different problems. So today we're going to do, of course, the trigonometric integration. Now some trig integrals are pretty straightforward. So if I say what's integral of sine x, I don't think you guys would hesitate before saying it's negative cosine x. If I say what's integral of cosine x, you would say, well, that's sine x. So that's not too bad. If I give you integral of sine x cosine x, you would say, oh, I'm going to let u be sine x. du is basic substitution from section 5.5. du is cosine x dx. And then this part is going to be your du. So you get integral of u du, which is 1/2 u squared plus c, which is 1/2 sine squared. Now let's deal with powers of these functions. For example, what happens if I have now, I have a breakdown of powers, even powers and odd powers, but let's go with odd powers first. What happens if I have sine cube x dx? Well, the best way to approach this is to write it as sine square x and then sine x dx. So peel one of the signs off and then convert the other even power sign, which is kind of, because if you have odd power and you take one sign out, what you're left with would be even. And for evens, we can convert sine to cosine. And then I let u be cosine. du is negative sine. So it is 1 minus u squared du, and then there's a negative pops up because it's negative. So I get negative integral of, u minus 1/3 u cubed plus c, which is 1/3 u cubed minus u plus c. And u was cosine, so it's going to be 1/3 cosine cubed minus cosine plus c. So that's how you handle odd powers. Same thing with cosine cube. You just do the same thing. You peel one of the cosines, convert the rest into sine. What if it was like 5? Well, it's doable, but it's not pleasant. So sine to the power, I still peel off one of them. And then the 4 becomes sine squared. You can always do that because it's even power. So you can write it as squared to some other power. Then I let sine squared, I convert it to 1 minus cosine squared. And then I do u sub. Let u be cosine x, du is negative sine x dx. So this becomes negative 1 minus u squared du. And the negative comes because of this negative. So no choice other than foiling it out. So you get 1 minus 2u squared plus u to the 4 du, which is going to be negative u minus 2/3 u cubed plus 1/5 u to the 5th plus c. And don't forget to go back, plug back in your u equivalent, which is cosine. And if you want to just make the adjustment for the sign, you can just push the negative through. You can write them in the order that pleases you. And that's how you handle this. So odd powers of sine or cosine, you always peel just one of them off. That's going to give you your D part. And the remaining would be an even. So you can write it as either sine squared or cosine squared to some power. And I'm not going to finish up this integral, but let me just show you, like, for example, if it was sine to the 17th power, which you're not going to get this on the test. You're probably not going to see this in life. It's just, this is not a very something commonly done. But if this was the case, then you still peel off one of them. This is going to give you a D part, and you're going to convert sine to the 16 as sine squared to the 8. And sine squared, you're converted to 1 minus cosine squared. And then go proceed by doing a U substitution and so forth. So it's not the end, but that's just the main part is done now. Okay. So that's how you handle odd powers of either sine or cosine, either sine or cosine. Okay. Now, even powers are a little bit trickier when it comes to this. It's not tricky as much as it is. Some smaller even numbers are okay, but once you get to big even powers, it's going to be a little bit unpleasant. So for example, if I have sine squared x, even power, very good. What we do is we use what's known as the reduction of power formula. And let me remind you what the reduction of power was. In trigonometry, we talked about sine squared is 1 minus cosine of double angle, and cosine squared is 1 plus cosine of double angle. So this is going to be 1 minus cosine of 2x over 2, 1/2 1 minus cosine 2x, 1/2 x plus integral of cosine, minus integral of cosine 2x dx. Now I could have done this directly, but let me explain how I'm going to integrate cosine of 2x. I'm going to let u be 2x, du is 2 dx. So what I'm going to end up with, 1/2 integral of cosine of u du. And so that the cosine is sine. And that c is now a different c, but still does the same job. It's a constant. And then I replace u back with 2x. So that's how you handle the even power of sine now, or cosine. Same thing with cosine. If it was cosine, you would use the second identity. Now, if it was sine to the, say, 6, as I said, this is not pleasant, but if it was sine to the 6th of x, you still can do this. You write it as sine squared to the 3rd. And then for sine squared, you write it as 1 minus cosine 2x over 2. Yeah. And then, of course, 1/2 cube is 1/8. And then you have to cube what's inside. And then you integrate each one of them. This one, you again have to do that reduction of power formula for this. So it's going to be messy. And as I said, it's outside the scope of the test, but yeah, you can do that. If you see that, then this is a process you would have to do. Write it as some squared to some power, and then, yeah, do the reduction of power formula. Okay. Now, what about mixes? What about sine mx, for example, cosine nx? Can we integrate something like this? Well, it depends on powers of m and n. If either m and or n are odd, let's look at the following. Let's do an example. An example would show you how to handle this. So, for example, if I have sine square x cosine cube x, something like that. One of them has odd power or both. If it's both, then you figure out which one or decide which one you want to do this process to. But if it's just one, then your life is a little bit easier because you can just do that one. What I'm going to do is I'm going to peel off one of the cosines, whichever is the odd one. And again, if it's both, then you pick which one you want to do. But whichever is the odd one, you peel that off. This is going to give you your du, which means you have to convert the remaining of it to the other function. So I change the remainder of cosine squared to 1 minus sine squared. And now I can just let u be sine. I don't even have to expand it. I can let u be sine x. Du is cosine x dx. Now that becomes u squared 1 minus u squared du. And then, of course, I can FOIL it now. I mean, distribute it now. And then plug back in sine. Okay. So if at least one of them is odd, you can peel one of the terms of it, one of the factors of it, and then convert the even portion of it to the other function, whatever that other function is, and then do the integral by substitution and such. So it's not too bad. So at least one of them, either m or n, has to be odd. If both are odd, you decide which one to peel off. Usually I will go with the smaller one. I peel off the smaller, it's easier to convert them to the other function afterwards. The one that's a little bit less pleasant is if they're both even. Then what you need to do is you have to do reduction of order, but I suggest first convert them to the other function and then do reduction of order. Although you could just do reduction of order as is, and then go through that. So it's up to you what you choose to do. But basically, you have really no other choice than reduction of power. So I can change this to 1 minus cosine square. And then, yeah. And then do reduction of order on those two. Or you could have just done reduction of order on each of those and then take it from there. As I said, this is not a very pleasant problem, but this is at least something to do, a way of doing it. So if I did it this way, I would get 1 minus cosine of 2x over 2, 1 plus cosine of 2x over 2, but then you have to square it because it's to the 4th. Then, yeah, square it, FOIL it, and see what happens. It's not pleasant. So this is how you handle sine and cosine. Think of the powers of sine by itself, powers of cosine by itself, mix sine and cosine with different powers. So this is how you handle in those. Next, let's see what happens to secant and tangent. How do we integrate secants and tangents? So first we do the single functions and their powers, and then just like sine and cosine, and then their powers, and then their combinations. So we have all those possibilities. Let's start with tangent. I think tangent, you guys, so integral of tangent, and again, I do secant and tangent. You can equally do it for cosecant and cotangent, almost the same steps, but with cosine and cotangent, a lot of times you end up with a negative sign there that you have to deal with because they're antiderivative form. So suppose I have tangent x dx and I want to integrate that. The best thing to do is I write it as sine x over cosine x. I let u be equal to cosine x because that's my denominator. Du is negative sine x dx. Good, that's the top. Now u was cosine. So this would be an antiderivative tangent. You can memorize it, you can use it if you need to. But you could have another form of it because you can put the negative as the exponent of cosine. And cosine to the negative first power is secant. So these are both acceptable form of the antiderivative of tangent. Secant gets a little bit trickier. In fact, secant, unless you have seen it before, it will be very hard for knowing the trick that's involved in calculating antiderivative of secant. So antiderivative of secant x, to calculate that, actually you have to, again, I don't know if you have seen this before, but I hope you can remember it. You multiply top and bottom by secant x plus tangent x. And again, I don't know how would you know this unless you have seen this before, but that's what you need to do. And then you distribute it out. Then I let the denominator as I would normally be my u. But notice, what would du be? Derivative secant, which is secant tangent, and derivative tangent, which is secant square. And that literally is what I have on the top. That's literally what I have on the top. So it's going to be integral of 1 over u du, yeah, no surprise, which is natural log of u plus c, which is natural log of secant x plus tangent x plus c. So integral of secant is in natural log of absolute value of secant plus tangent. So we know now how to integrate tangent, and we know how to integrate secant. Now we need to look at the powers of each of those separately, and then the combination of the two. Okay. So let's go with even powers of secant first. So even powers of secant first. So integral of, say, secant to the 4x dx. So for secant to the 4, I write it as secant squared times secant squared x dx. Always, instead of peel 1 as you did for sine and cosine, here you peel 2 for secant. So secant squared. Now if it was secant to the 10, you write it as secant to the 8 times secant squared. So they should add up to 10, but you peel 2 for your d part, and then the rest you have to do what I'm going to tell you to do now. So I'm going to convert the rest of secant squared to tangent. Remember, the formula was 1 plus tangent squared is secant square. So secant square can be replaced with 1 plus tangent square. That's a trig identity. And then now I can let u be tangent. Du is secant square. So that's du, that's u. And u, of course, as promised, was tangent. And that's how you do it. As I say, it doesn't matter what power of secant it is. If it's even, you peel 2 and convert the rest to tangent. And you let tangent be your substitution, your u. So again, if it's an even power, you peel 2 to create your du, convert the remaining, which also going to be even power, to tangent. And you let u be tangent of x. Okay, so even powers of secant, unlike sine and cosine, which even powers were unpleasant, for secant, even powers is actually not too bad. Now, how about odd powers? What about secant, say, cube of x dx? We're actually going to be very careful and not go too far with this, because if I go into secant to the 5th, 7th, 9th, or whatever, what the solution is, it actually kind of takes you from 5th to the 3rd, and then you still have to do what I'm doing here for the 3rd to go from that to the solution. Right. So it's one of those things that it's recursive kind of thing. So it's probably better to just focus on, like, say, low powers like 3 and see how that works. So actually, this is part of one of the fun ones. So what we do is we're going to split it, as you would probably guess, as as a secant x, secant square x dx. So that's a first split. Then I'm going to do integration by part. I'm going to let u be secant x, dv be secant square x dx. That makes v be tangent x, and du be secant x tangent x. Okay. So now my integral becomes secant x plus tangent x. Sorry, secant x tangent x, no plus, minus integral of secant x tan square x dx. Okay. Now I'm going to convert tan squared in something in terms of secant, which is tan squared will become secant squared minus 1 push that through. Right? Now remember, secant cube is what I wanted, right? So I take it to the other side. Now I know how to calculate. So again, I just took that to the other side. I know how to calculate this from from recent lectures. So and then divide by 2. There's always a plus. Yeah, sure. So that's how you do with secant to the 3rd. Now, again, there's a trick for secant to the fifth, seventh, ninth, and all those other odd powers of secant. But as I said, this is the kind of things, and I would say, well, let's just use a table of integration for this rather than having to do this, because all of those, they reduce from 5 to 3, then you have to do 3 to 1, just like this one, which is not pleasant, but they do give you okay information about how to do that process. Okay. Now, if I have a combination of secant and tangent, let's say secant to the mx, tangent to the nx, yeah, it's the same. Yeah. Depending on what your m and n are, again, just like before, it just kind of outlines how to proceed with this problem. Now let's do the first case. If m, which is power of secant, is even and n is odd, oh, sorry. Yeah, no, not this. Sorry, my apologies. Just n being even is sufficient. If m is even, yeah, sorry, but then I peel off 2. And this part and dx is going to give you a du, and you're going to convert the rest of secants to tangent. So let me tell you what I mean. So if I have integral of secant to the 4x tangent, it doesn't matter, to the square x dx, it doesn't matter, it could be even, odd, or whatever. Then I'm going to peel 2 of the secants off, combine it with the dx. This is my du, and then I'm going to convert tangent to secant. I'm sorry, I'm going to convert secant to tangent. I'm going to convert secant to tangent. I'm too much stuck on the sine cosine right now. I'm going to convert secant to tangent. My apologies. And then obviously the secant squared x dx still is going to be there, but it's going to become my du because I'm going to let u be tangent. And then do the power, do the antiderivative, and then convert u's to tangent that it was. Because there are a sequence of equalities here, of course. Okay. So that's how you handle when m, the power of secant, is odd, I'm sorry, is even, that's what you do. If n, the power of tangent, is odd, then you do the next thing. So if power of secant is even, you do this, you peel 2 off, convert the rest into tangent, and then do u equal to tangent. If power n of tangent is odd, let's do this with an example. So this is n, this is odd. I'm going to peel off 1 secant and 1 tangent. And then I'm going to convert the rest of the tangent to secant. And why is that? Because I'm going to use secant to be my u, and du is secant x tangent x dx. And then, yeah, you just do the same thing as you did before. And that's how you handle whenever you have power of tangent is odd. This is how you handle when it was power of secant is even. But of course, there is a third case where neither of those are true. Now, if they're both true, you pick and choose which one you're more comfortable with doing and which one has smaller powers. But if neither are true, if power of secant is not even and power of tangent is not odd, so you have some like secant cube x tan square x dx. In this situation, you convert the even power one, which is tan, into secant. Now you're like, well, this is not very friendly. Yeah, I know. Because now you have to calculate the integral of each of the secants, which, as I said, secant q was already hassle. Now you have to do secant fifth as well. But fifth goes to 3, 3 will go to 1, and then you know what 1 is. Okay. So that's basically trig substitution. This is how you handle integral of trig functions. It's not something you want to memorize, because if you try to memorize those, there are too many different cases, and just recognize the pattern and know how to handle it with different combination of numbers. It does amount to memorization, but you don't want to focus on just memorizing it without knowing where things come from or how you come up with things. So that's going to be a little bit dangerous. In the process of showing this, I actually showed you guys some examples. So hopefully as you review this, the examples will make sense and you understand how to handle them. But if not, again, just please let me know what problems or examples from the book you would like me to look at for you, and I will do that this week in my future videos of the week. In my next video, I'm going to talk about trig substitution. And depending on how many problems, if I'm given by you guys, I may do some of those in that day as well. But I'm going to talk about trigonometric substitution, which actually is a pretty pleasant and clever method. So I hope you guys appreciate it. And then we're probably going to discuss also the partial fraction decomposition method, maybe this week or maybe early next week. We'll see. We'll play by ear, see how we're doing. Okay. Do spend time on the homework for this section, because practice does make perfect in this, or at least eases you into the topic. But yeah, and then we'll see how to answer some of your questions in my next video. Okay. Again, thank you for your attention, and I will have my next video prepared for you guys for next day or two.